All right. Well, I think we should start. So welcome everybody to the N3C Community Forum. It's May 2nd, well over 2 years after the beginning of the pandemic. We've really been doing this for a while. So announcement, upcoming N3C Community Forum presentations, which we'll go on describe in a couple minutes. NIH needs feedback, so we have a nice link to a survey, which people could do. That would be fantastic. And today's presentation topics will be Brad Price and Maryam Khodaverdi will be talking about practical machine learning for COVID-19 using EHR data, an N3C case study. And it's really striking how much more machine learning, deep learning work there is now than there was a year or two ago. And Phenotype 4.0 by Emily Pfaff. And so we have a TBD for next week. 16th, use of cardiopulmonary exercise testing and addressing issues like fatigue in pediatric PASC by Dan Cooper. May 23rd, outcomes in COVID-19 in people with hemophilia, and the monthly Recover Long COVID project team updates. And that's really quite remarkable. It's quite a testament to having, so we have 4 million COVID positive patients, that it's possible to subset the data for not terribly common diseases and still, I'm sure, get a large enough N to do interesting things. I think that's a good really use case of the effectiveness of having such a large repository. May 30th is Memorial Day, and June 6th, highly effective protocol for treating long COVID patients that either completely resolves or significantly improves symptom burden. So we're up to about 5 million COVID positive cases with 13.2 million people in the whose records are in the enclave. And so Brad, I think you're going to be sharing slides, and you and Maryam, looking forward to your talk.
Awesome, thank you so much. Let me go ahead and get the presentation up here, and then everybody see my screen okay? No, that's probably the most common question asked in the past 2 years.
Yeah.
So really appreciate everybody's time today. Really appreciate y'all attending the talk. This is something Maryam and I and a much larger team have been working on for a good little bit now. And we've started to find some interesting things, talk to you about the bigger picture of what we tried to do here, and kind of get into how we've been using machine learning to kind of define the best treatment for COVID. And I'll put best in quotation marks, because what you're going to hear is a story about how we view the best and the way we've been trying to study it. Want to give acknowledgments to our entire project team. One of the best things about working on N3C has been the researchers I've gotten to meet, and we've got them from all over. Jared, Tim, Jeremy, Bill, Sally, Maryam, Wes, Hamadraza, Sharon, Zach, Susan, and Mike. This has been such an awesome team to work with everybody bringing such good ideas, and I think is really a truly statement to what happens when you have team science and a team science approach. Clinicians, statisticians, informaticists, all coming together to try and solve a problem is a really big deal. So I want to thank each of these people individually, but really want to say none of this work would have been as good or as interesting as it is without everybody's perspective here. So we're gonna talk about two different projects, actually. The first thing we had to do when we were trying to define a best treatment for COVID was define an ordinal severity scale. We had to come up with what's an outcome, how do we start looking at the problem, those type of things. So we're going to introduce this severity scale to you and kind of let it drive how we're going to analyze data and think about data. So Maryam's going to introduce that to us and kind of talk us through that. I'm going to get into some of the machine learning concepts we've used and some of the problems and some of the issues we've run into. and start moving that direction. And then we'll get at the question, is there a best COVID-19 treatment for hospitalized patients? And then have some time for some questions at the end. So Maryam, do you want to go ahead and take over?
Yeah, thanks, Brad. So early in COVID-19 pandemic, WHO proposed and created clinical progression scale or Ordinal Scale OS to measure outcome for clinical studies. But the use of WHO OS is problematic when we look at electronic health record EHR data. So what we did, we developed an OS of outcome that could be applied to real-world COVID-19 EHR data. More specifically, we use OMOP Common Data Model to develop our OS. We also access visibility of our developed OS to describe COVID-19 outcome in EHR data contained in N3C repository. WHO OS is presented on left. One feature of this OS is that it actually covers all patient status from uninfected to ambulatory, all the way to death. And they also assign a score 0 to 8 to each of their level. Next slide. This slide shows the WHO OS and our proposed EHR Ordinal Scale for COVID-19 severity. We suggested 6 different levels, started from outpatient, and then those who hospitalized, oxygen use, mechanical ventilation, ECMO, organ support, and death. Next slide, please. One feature of our OS is that we can calculate the OS level for any time step that a study needed. We can calculate it daily, we can calculate it weekly, and if we have enough data and information, we can calculate for each hour. So what we did for the first plot, we consider 4 million, approximately 4 million COVID positive patients that are available within N3C repository. We find our first day of COVID-19 diagnosis. We follow those patients for 28 days. For each day, we calculated the OS level. And then you see the x-axis is the day, and then y-axis is number of unique patients. As you see here on left, most of the patients are in level 1 outpatient. So in the left, in the right, in the second plot, we have hospitalized patients, those who hospitalized at least for a day within the first 28 days. Again, y-axis is a day, x-axis is a day, y-axis is a unique number of patients. And we see that most of patients tend to get improved and transfer to OS level 1 outpatient. We see that as days increase, we see increasing the number of patients in level 1, and also number of patients in other levels 3 to 11 are decreasing as days increase. Next slide, please. Another feature of Ordinal Scale is that we can use our OS level for input or early stage of our patient as well as outcome. For example, here we have like week 1 as like input, and then week 4 as outcome of our patient or our cohort. Actually, this table are compared. In this table, we are comparing the distribution of OS for second quarter of 2020 with the first quarter of 2021. And we find out that the distribution is significantly different for these 2 quarters as well as other quarters. Next slide. Back to Brad.
So getting a little bit deeper into Maryam's point here is what we've really developed is an ordinal scale that allows us to break up a patient severity and look at a single patient severity over time. We can use it as stratification to kind of look at different treatments based on levels of severity, but we can also use it as an outcome. Now, one of the things we were most interested in, and one of the real reasons that drove the creation of this ordinal scale, was to investigate a 28-day outcome on patients. So a 1 month, 4 weeks outcome on patients. So that's part of the reason you see us break it up into week 1 and week 4. One of the things we're going to look at is that 28-day outcome. But again, I'm a statistician. I work in a lot of software stuff. And so the phrase I'll use, it's a feature, not a bug. It's a feature because we can use this ordinal scale in multiple ways. We can use it to define cohorts, but we can also use it as the outcome itself, just on different time points inside of a patient's history. So why did we want to look at machine learning for this anyway? The basic objective here was efficacy and safety of various COVID-19 treatments have usually been studied with prospective randomized clinical trials, what we're going to just abbreviate as RCT. However, the limited sample sizes of RCTs often limit their utility, especially for subsets of patients. Retrospective analyses using very large data sets enable investigation of various therapeutic outcomes among patients with differing levels of disease severity. This study seeks to find the best therapy or combination of therapeutic agents for subsets of patients with various levels of COVID-19 disease severity. What better place than N3C? What better place are we going to have a massive amount of data that, looking at it from an OMOP perspective, looking at the data quality we have, looking at all the things that go together to start trying to see, can we get enough sample size help to actually use machine learning? Can we get enough data to use machine learning to start to get some insights? But like anything else, we run into some trouble when we start thinking about that problem. So let me take you through our thought process. Let me take you through what our groups discussed, because I think that tells the whole story. I think it provides a big picture of the approach we're going to take, but also gives you some background in some of the, I'll say, hiccups we ran into while going through this. So the question really comes down to, can we predict a hospitalized patient's 28-day outcome and understand treatment and clinical care practices related to this outcome? We decided the OS scale, so the outcome of interest should be based on severity. How are we going to define severity? Now, our OS scale can do it for any time period. We can do it daily, we can do it weekly, we can do it, however you want to break this up. If we look at daily variation, there's some problems that can be caused just because people jump around a little bit. So one of the things we approached, or one of the ways we approach this, I'll say, is we looked at a weekly severity. So kind of that last table I showed you where we look at a week 1 severity and a week 4 severity. Now we define week 1 as the first 7 days. We define week 4 as the last, so up to day 28, right? The 7 days preceding day 28. So we're going to look like at a weekly ordinal scale. Now, this comes down to an outcome as well. So in machine learning, we're going to try and predict an outcome. It's one of the ways I tell people to think about machine learning from a very low level perspective is it's a predictive model. We're trying to predict an outcome. So for us to do that, we've said the outcome should be based on severity, but should it be the severity itself? Or is it binary? Is it a patient was discharged or not? Is it a decrease in severity? So if we're going to define a patient to be starting in week 1 at an ordinal scale where they're hospitalized, should it be discharged? If they're on a ventilator in week 1, should it also be discharged or should it be any decrease? So the patient is moved off the ventilator. So there are a lot of different ways we can define severity and start thinking about what an outcome variable looks like. So again, it comes down to, is it understanding transitions through severity? And then there's a lot of covariate issues that come to play. We start looking at BMIs and we know the impact those have. We look at comorbidities, we look at vaccinations, we look at the variants we've experienced throughout this, throughout the pandemic. And then the other piece that brings up is time. All right. So when we used N3C for this particular study, there were about just 3.7 million infected persons from 69 centers. We used our ordinal scale, and then we set a baseline ordinal scale for each patient as the maximum ordinal scale that occurred the first 7 days after COVID-19 diagnosis. So what you can think about that as saying is we broke up our study and our patients into cohorts. We split it up and said, okay, if you're an OS level 3, we're going to study you separately from an OS level 5, from an OS level 7, from an OS level 9 during week 1, because we thought your severity affected the treatment and the approaches clinicians would take, right? So we wanted to make sure we could study that. We used the CCI, so the Charleston Comorbidity Index, to measure the number of comorbidities. We looked at other factors such as, is your age greater than 60 years? What's your ethnicity? The quarter of diagnosis, just to see the time effect. And certain treatments would be considered independent variables. Now, when we talk about treatments, what we're going to talk about is we're going to talk about anticoagulants, we're going to talk about steroids, we're going to talk about antibiotics, we're going to talk about targeted antivirals, and we're going to talk about 2 types of monoclonal antibodies and also a miscellaneous group that included all other treatments. All right. So data we're looking at, we're only going to look up to or through Q4 2021. And we're going to break the data up into 2 time periods. And I'm going to give you a little discussion of why and some of the stuff we've experienced. We're going to stratify by time, basically making 1 time period before Q3 2021 and 1 time period after Q3 2021. So Q3 2021, Q4 2021. Why? This is going to investigate the effect of Delta variant and if it changed any treatment efficacy, all right, to see if anything happened there. Now, at the time of analysis, and we're starting to investigate Omicron now that kind of data is catching up and we're getting the sample size we need to investigate Omicron. So we're starting to move that way as well. And let me give you a little picture on why. So this is some data we have access to through a different project we're working on. And this is the variants that were in West Virginia at different times. I'm at WVU, so I have access to some West Virginia specific data. So I thought I'd share it with you just to say, if we look at Alpha here, then we see Delta start to rise and Omicron appear as well. We can break these up into distinct time periods and look at the efficacy of different treatments against it. So what we're going to do is really stratify. We're going to stratify between Delta, which would be Q3 2021 and beyond, and prior to Delta, just to see if efficacy changes, just to see if the treatment impact changes, just to see how everything would work and move. So as we come through this and as we start looking at the bigger picture here, let me walk you through how we decided to determine the best treatment, all right? Given the complexity of inputs and outputs, machine learning is what we're going to call the quote unquote ideal strategy to assess impact of outcomes among various subgroups of patients. We talked about how we're defining the baseline and the stratification. What we're going to define as the outcome is the probability of moving from a higher OS level or a more severe disease, I apologize about the misspelling, to OS1 or the outpatient at week 4. So what we want to do is we want to understand how people have transitioned through, but we're going to define the best treatment. And what I'm going to present to you as the best treatment as what takes a patient from their week 1 maximum OS level to outpatient by week 4. What's the ideal strategy? And we're going to stratify by CCI. So anything I show you, we're going to show as CCI changes, how those probabilities change. Now, after talking to clinicians, and I talked a little bit about the team science before, after talking to some clinicians early on in this process, what we wanted to do was kind of look at standard of care. So in this model, what we've tried to build in is a standard of care metric. So if a patient begins in week 1 in OS3 or OS5, so hospitalized and on oxygen, we assume spike monoclonals were given, okay? If they're on OS7 or OS9, so mechanical ventilation, and in this case, OS9 is organ support and pressors, what we assume is steroids were given, all right? Now, we thought about a lot of different methods, and we actually tried a bunch. But the model I'm going to present to you is an elastic net penalized multinomial logistic regression that looks at each of the different OSs. Now, why do we do this? One, we need to balance interpretability of the model. We need to make sure any insights we provide, there is some standard, I'll say, statistical interpretation. So we wanted to kind of restrict our view there. There are other methods out there that we've tried and some things we're currently working on in this group as well to use some deep learning algorithms and different type tools to get after this problem. But we wanted to start here where we could have an assumed, how do I want to say this? We can assume some different things and get a probability as an outcome. So what I'm getting ready to show you is a plot that looks at the probability that you achieve this week 1, or excuse me, an outpatient at week 4. You become an outpatient at week 4, conditioned on what treatment you were given and what your week 1 OS was. So just to kind of walk you through the plots here, because this is where some things get interesting and some things start to look a little, and again, this is working, still a work in progress. We're digging in every day just a little bit more. So just to walk you through the plots, top row is Q2 2020 to Q3 2021, what we're going to call pre-Delta. And then the second row is Q3 2021 to Q4 2021. Each of the columns, this first column assumes your week 1 was OS3. Second column, OS5 at week 1. Third column, OS7 at week 1. Column 4 is OS9 at week 1. Each panel, the y-axis corresponds to the probability of a OS1, so an outpatient outcome at the end of a 28-day period. Each of the lines correspond to a specific treatment we analyzed. And again, a red line would be anticoagulants. A green line is macrolide, and I apologize, I'm not a clinician, so sometimes the pronunciations gets me. We're looking at the set of antibiotics. The blue line is spike protein monoclonal antibodies. The pinkish line is targeted antivirals. The gold line is immunomodulators, antibodies. The light green line is miscellaneous, and the purple line is steroids. So as you come across, you can see some changes. So you see a high probability if you start at OS3, this is just hospitalized, no oxygen. If you start at OS3, we see pretty good outcomes just from a probabilistic perspective, all right? This is a probability of 1, down here would be a probability of 0. So we can see our probabilities up in the mid-90s. We see the top here would be a use of steroids and spike monoclonals. We're assuming that spike monoclonals were given to anyone who is in OS3 or OS5. You can see pretty good outcomes for OS5, but one of the things that you see trending across is this gold line that stays low, which is the immunomodulators. We did not assume you were given spike monoclonals and immunomodulators at the same time. That was the one place we did not assume, and we tracked back through the data to make sure that assumption was correct. And in most cases, I think throughout the entire N3C, we only found that occurred less than 100 times. So one of the things you see as you kind of look is you see different treatments have the highest probability of success, or what we'll call success, which is reaching OS1 or an outpatient status at the end of week 1. But one of the things you see is it's a different treatment for each group. For OS3 and OS5, it's spike monoclonal antibodies plus. For OS7, we're seeing steroids plus. And one of the things we're seeing, which is fairly interesting, is this mixture of spike monoclonal with steroids on OS7 and OS9 having fairly good outcomes. Now, one of the things I'll have you look at, apologies, one of the things I'll have you look at, and one of the places I'll move your eye to is while we look at it across the severity scale, let's look at it between time periods as well. Let's look at that actual effect of the Delta variant and say, look, if it worked for OS3 pre-Delta, did it still work during Delta? Well, one of the things you see is as we transition from a pre-Delta to Delta, we see a change in effectiveness. So here it would be steroids plus monoclonal antibodies, where here what we're looking at is during Delta, it's targeted antivirals plus spike protein monoclonal antibodies having the best outcome. And as we continue to move across, we see in each of the groups a similar response. We see there is no consistent one-size-fits-all best treatment. The stratification on severity and the stratification on time seem to have worked well. Now, there's a lot going on in this plot. There's a lot to think about. There's a lot of moving parts. So one of the things I just wanted to take a second and do was kind of summarize what we saw. So if we come in here and we just kind of break this down, and just to give you the major takeaway, right? Your one takeaway from this, if there's one thing you remember about these results, just here's our ordinal scale levels, 3, 5, 7, 9. Here's the description. So this is hospitalized with OS3. This is starting at hospitalized, all right? This is pre-Delta, this is post-Delta, all right? So we see, and that is off, and I do apologize about that. This should say steroids. So what we see is a change. We see steroids to antivirals. From an OS5 perspective, we see spike monoclonal antibodies only worked best pre-Delta. Post-Delta, so during the Delta era, it was anticoagulants with spike monoclonals. We see steroids plus, and steroids only work fairly well for OS7. We see steroids and anticoagulants and steroids plus spike monoclonals do fairly well during the Delta area. And again, for OS9, we see steroids plus spike monoclonals work well in both. And again, we see it show up here. So there are some trends that can be depicted for this. We can see some trends depicted through this as well, where we're seeing this interaction of steroids and spike monoclonals do fairly well and have high successes. But if you go back here and look at the probabilities in general, you'll see there's fairly high probabilities for at least the low severity groups. Now, other interesting results we saw. The first thing, and again, the major takeaway, across all baseline OS levels, not one standard combination of treatments provides the highest probability of hospital discharge at week 4. It's not a one size fits all problem. Clinical severity matters, the approaches matter, those type of things matter. As we get into the models, and again, this makes some assumptions about what was given. As we get into the models and actually start looking at the coefficients, which is one of the advantages of using a traditional just penalized regression model, right? Something that we can understand, something that's taught in, a graduate level stats course. What we find is being male and older than 60 years of age are associated with lower probabilities of hospital discharge by week 4, so worse outcomes. A higher CCI in any case is associated with a higher probability of death by day 28 or by week 4, and lower CCI values lead to a higher probability of hospital discharge, except for those starting at OS level 7. OS level 7 is ventilators. Variants influence the most effective combination of therapeutics, which is something we're going to continue to study. And like I said, we're getting into the Omicron data now to start seeing what's going on around there. Now, just like any study, we have conclusions and limitations. These data suggest the optimal therapeutic agent choice may be guided by the level of disease severity and presence of specific SARS-CoV-2 variant. The assessed treatment regimes confirm previously identified treatments, but it also suggests the potential for positive impact of other treatments. That's one of the things we're continuing to look for, and we think that's one of the powers of machine learning is as we go through this and as we break down, because I just showed you what got you to discharge, the most likely combination to get you to discharge. But there are combinations that will say this is what would most likely get you to just hospitalized without oxygen. That's a big step coming off a ventilator. So again, as we look at this and as we continue to look at what's going on, there's a lot of insights to be found in these models. It's a retrospective analysis. Unrecognized confounding may be present. We only have access to the data we have access to. We're trying to figure out as much as we can from it, and that's the power of N3C, but we always have to acknowledge there could be something there. And again, I'm a statistician, so pardon me for saying this, but this is a retrospective analysis. I cannot guarantee any causal relationships here. That's a different type of study and something we're very interested in doing and kind of helping motivate it. But this is to me, this is part of the power of N3C, is we can use studies like this to help design clinical trials. We can use studies like this to kind of motivate what's that next thing we should be investigating? How should we look at this to scale? And again, I just want to, give a couple of comments, and Sally Hodder helped me, help put these together. And this is similar to something I've heard her say a few times, is N3C has just outstanding power for team science. That's one of the things I think has really shown me during COVID and I think has really kind of driven the research and the science forward is team science works. You have a lot of smart people working on hard problems and working very hard at trying to address these questions. I think N3C is a model we should be looking at for future pandemics, but also for, the health problems that we face. I think the data sharing agreements, especially as a statistician, I love it because it gives a larger picture. It gives a great picture, and there's a lot of power in the data we have. We have done a study, and this is a study that came out of the group Fryer and some of the researchers. One of the things we want to point out, especially living in West Virginia, is rural populations suffer a higher COVID-19 mortality. And this has been found, but one of the things we're going to continue to look at, that's a cool paper that should be coming out soon. And then what did we really do? We developed an ordinal scale and then we came up with kind of our approach to detecting what's the best treatment and what type of studies we should be looking at. Again, we want to thank everybody from N3C. We're, if you can't tell, we're big fans of the platform. We're big fans of the tool. And here is the acknowledgements page for the NIH. So with that said, we really appreciate your time and thank you so much. And please let us know if you have any questions.
Well, thanks. This is great. So Harold Wayman asks, how does one communicate uncertainty in those curves? It's not sampling uncertainty, but other uncertainties. Also, does it matter that treatments went through fads over time?
That's part of the reason we're adjusting for time. We adjust for looking at the different, I'll say, clinical practices, and it brings up an interesting point and something we're looking into a little bit around the use of pressors and looking at how pressors have been used in different time periods. Those curves can express uncertainty in a lot of different ways. In in a short talk like this one, where we're talking about a general idea, I would tell you any type of probabilistic curve expresses uncertainty. But we're also looking into how we would obtain p-values. And again, in regularization, especially in GLM frameworks, that's still an open question to the machine learning community. So it's something we're working on pretty rigorously, is how do you do post-selection inference to make sure we have, I'll say, bounds on some of these probabilities we're sharing and some of the coefficients we're sharing as well.
So with respect to uncertainty, two questions I'd have. One is, give us a sense as to how many variables you're using. Obviously, N3C has a huge amount of data. How much of this, how many different data elements are you using in these predictions? Start with that.
So in the ML models, we started pretty big. I'll be honest with you. We tried to use everything that we could get our hands on. It's what I teach my students, is I call it the kitchen sink model. Throw everything in the kitchen sink at the problem, see what you can come up with to get your first approximation. Right now, I'd say we're working on a subset, because we went back to kind of first principles of statistical modeling, and don't model anything you couldn't explain. Don't model anything you couldn't provide an insight for or try and justify in a talk like this. Between, one of the nice things about using a multinomial and using a traditional regression framework for it is we can create interactions. We can look at things that clinicians would suggest that should be interactions. With interaction variables, we're at 6 different OS scales. We have probably 20 to 25 variables. So again, we're using age as a binary state, whether you were over 60 or under 60. We're using CCI to track comorbidities, so the Charleston Comorbidity Index. We've had some problems with some missingness in the data, specifically around BMI. So we're using CCI as a proxy, as it does include BMI. We're using ethnicity, so that adds a couple different interaction variables. And we're also using the interaction between these treatments. So we created a variable that does all two-way interactions with what we were assumed to be given. So for OS3 and OS5. So I'd say per response, we're at 20 to 25 variables, and then putting some automatic feature selection over the top of it to make sure no noise is getting through it. So just a little bit of L2 regularization.
And then in terms of treatments, now obviously, it sounds like from what you're saying, you're imputing a certain number of treatments, and obviously modulo a lot of missingness. You've got that also in the data. So
Yeah.
what's your kind of approach to dealing with that?
So I'm lucky to have some really smart analysts working on this project with us, like Maryam. And one of the things we spent probably the first 2 to 3 months of this project doing was going through those. And Maryam and Jared and Jeremy and Hamadraza, Tim, myself, we spent a lot of time digging through data and looking at missingness and trying to figure out what the effect of missingness would have, how it looks at subsets and different things like that. And I would say they came up with diagnostic sets to create the OS and the treatments, because if you look at our treatments, we're rolled up pretty big. And when the paper comes out, and hopefully the paper on the OS scale isn't too far away, when it comes out, you'll see how we kind of rolled it up to say different sites have different protocols. They may have different concept codes or the concept sets that were used. We took a lot of care in that. We're not doing a ton of imputation behind the scenes at this point. Just trying to look at how different sites, and again, this gets back to the treatment, like the fad question, right? Like different places have used different treatments at different times. And I don't want to call it a fad because it was best practices at the time. It's what people clinically thought would work. And so from that standpoint, it's we've tried to take a lot of care in the clinical perspective and what would have been used and how it rolls up into a larger picture. Because to take this and break it to 8 groups with all the different treatment regimes that could have been used or different processes, that's no small task anyway. So we're always going back, and I would say we take a lot of care and we're very careful in that approach. So at this point, we're not doing a ton of imputation behind the scenes. We're trying to use the data that is trusted in complete observations. But I think the next phase of this is to see what imputation would do behind the scenes.
Great. Well, thank you. Really, really interesting talk. And I'll look forward to see how all of this progresses. I'm sure it'll progress well. So Emily, Phenotype 4.0.
Hey, so this is probably going to be a pretty quick update. I will share a very brief slide presentation. Give me just 1 minute to get it up. Okay, so it's probably been a long time since folks heard about the phenotype because our prior update of Phenotype 3.3 was a very long time ago. It was probably almost a year ago. And we honestly weren't planning on making very many updates to the phenotype, certainly not a major version update, other than to continue to keep up with the LOINC codes for the newest tests that come out, every once in a while. But with the advent of long COVID and the fact that now there is a ICD-10 code for long COVID, we knew that we did need to make a change to accommodate that. So I'm calling this a minor but important change, and it certainly was major enough to necessitate a major version change to 4.0 from 3.3. And the big change here is that Phenotype 4.0 allows U09.9, which is the ICD-10 code for long COVID or PASC, to become a strong diagnosis code and therefore an inclusion criterion. And just to back up for a second, to remind everybody that this phenotype is what all of the sites that contribute data to N3C run locally in order to define who their cohort is, then collect longitudinal data for that cohort, and then send that cohort and all that longitudinal data to N3C. And what we were missing with our prior phenotype that did not have U09.9 because it didn't exist yet, was any data for patients who ended up having long COVID, but for whom we did not, or a local site did not have the initial COVID documentation. So the phenotype was very focused on looking for U07.1, which is the ICD-10 for COVID, or a positive COVID test. Those were our two inclusion criteria before this time. And that's all well and good, and that really got us a very robust COVID cohort. But there are many patients who have long COVID that do not have that initial documentation of a positive test or a U07.1 code, either because they were never able to get that test if they were really early pandemic patients, or their test or their diagnosis code isn't in the records of the site that is contributing to N3C, but their long COVID code is. So it made perfect sense to allow U09.9, again, the long COVID ICD-10 code, to serve in the same capacity as a U07.1 code does in the prior phenotype. So I do think that this will enable a more inclusive cohort. It's not going to shoot up in numbers. U09.9 is not a hugely and heavily used code at this time from the analysis that we've done, but it will prevent us from excluding patients that should be in our cohort. We've also updated the LOINC list. So our previous LOINC list included a lot of quantitative LOINC tests, meaning they were tests that were intended to have a quantitative result as opposed to something like positive, negative, detected, etc. Without going into the weeds too much, our code was looking for those phrases, positive, detected, etc. And we knew that those phrases were never going to be the appropriate response for a quantitative test. And for that reason, we were increasing the processing time of our phenotype unnecessarily. And we want to make things as easy for the sites as possible. And so we pared down the LOINC list to remove quantitative LOINCs. This change should not result in a decrease to your cohort size. There is one institution that I'm aware of that may have seen that behavior, and I'm working with them. If you are aware that that is happening at your site, please let me know and we'll troubleshoot with you. But the intention is that your cohort size should rise. Now, we do know that cohort sizes are going to rise slower than they did in the past. And I don't know that I have a surefire answer for that, but my assumption is that it is based on at-home testing. So there's fewer people who are getting their tests recorded in their EHRs, so fewer new people are qualifying for the cohort. In addition to the phenotype, we have also updated the extract code, which goes along with the phenotype. And that extract code has been updated to accommodate some optional data enhancements that some but not all sites are participating in, all sites are welcome to participate in it. So I will tell you what those enhancements are, but not a requirement. So the enhancements that we are now supporting with our updated extract codes are the following. We are looking for indications of patients who went to a long COVID specialty clinic. And obviously this is only possible to add as a data enhancement at sites that have long COVID specialty clinics. So that's a subset. But that information is really helpful for us to figure out who may have had long COVID prior to the existence of the UO9.9 code. We've also built support for something that I know a lot of folks have asked for, which is admission, discharge, transfer transactions. And for those of you who aren't familiar with the ADT acronym, that is the idea that a patient is moving to different units in the hospital between admission and discharge, and each transfer gets an ADT record in the database to say this patient moved from emergency department to ICU to step down, each with timestamps. Mostly for us, that's really important so that we can determine who ended up in the ICU, but it's also good to just understand who came in through the ED and other details like that. So we're supporting that. We're also really excited to be supporting patient level social determinants of health. So the SDOH team has done amazing work with the area level social determinants of health that are available in the enclave. But some sites, especially those who have the EPIC social determinants of health module turned on, are able to support patient level structured social determinants of health. So things like a question might be, do you have concerns about having transportation to get to work, right? And the answer could either be yes, no. Those are all structured data elements that are often coded in LOINC, and we can now accept those data from sites as well, which will really add additional richness to our data at the patient level. And then we also are adding support for oxygen supplementation and ventilator settings for inpatient visits, and that will enable folks to know when you're doing research if the patients that were in hospital were on room air, they were on a ventilator, some additional details about the ventilator that will enable you to get to a greater level of detail about that kind of intervention. And then finally, led by Mayo Clinic, but our extract code is now supporting this, is if you are a site that has been engaged with Mayo on running the natural language processing pipeline that they've built in order to derive features from your clinic notes, our new extract code will accommodate you sending those derived features to N3C. So if you are not already submitting the above data enhancements and you are interested in doing so for any reason, you can always contact me, but you can also see more detail on our wiki where each of these elements is spelled out in great detail, what we're looking for, what we expect it to look like. There's a different design for each data model. A ton of work has gone into it. So I certainly want to thank the folks that were involved in designing these data enhancements, which are also members of the Phenotype team. And yeah, we're really excited to see these data flowing into the enclave. So that's all I've got.
Okay, fantastic. So no, that's great. Any questions or thoughts?
I see a question in the chat if I can send a link in the chat for the wiki, which I will do. So the link that I just sent is the wiki link, and the pages that you're looking for in the wiki that cover the data enhancements are all prefaced by new data element. And there's one for ADT, long COVID clinic. The ventilator one is called O2 device, social determinants of health, and then NLP.
So question from Signe Redfield, should patient representatives be encouraging LC patients attending clinics to request their healthcare providers update their records to include the UO 9.9 code?
It's a really interesting question. I will just say that based on the analysis that we've done, we have noticed that many of the long COVID clinic patients do not have a UO 9.9 code. And certainly the more patients that do have a UO 9.9 code, the more accessible those patients will be to, I would say, these kinds of phenotypes that we rate to try to identify patients with long COVID. That's not to say we rely solely on the UO 9.9 code, but I think that the more structured data that a patient can have coded in their record, the richer their data will be for phenotyping, and the more likely it is that they will be identified in work like ours.
Sort of an interesting question. It's maybe a little imponderable, which is if a patient or anybody goes to a provider and says, change my coding, most providers, I mean, most physicians would have, no idea as to who even to ask. Send an email to the coder. They wouldn't know the coders even are. I mean, it's an interesting question. It sort of is a HIPAA-ish thing. I imagine if you actually knew who to ask, you could say, you need to correct my record, and I imagine they'd have to, but most people wouldn't really in a healthcare system know what the entry point is for that sort of thing.
I mean, including me, I work with these codes all day long, and I would have absolutely no idea how to change my own record to add a code. So I think it's a fascinating question.
Yeah.
I do notice another question in the chat from Peter saying how do we get access to the NLP derived features? So that should be available in the Enclave data catalog, but not quite yet. So we have right now all of these new data elements from the sites that are providing them are flowing into the Enclave, and our data ingestion and harmonization engineers are hard at work processing those data and getting them staged for public consumption. That work is ongoing now and will probably continue for the next couple of weeks. And then once we have at least, I want to say it's at least 5 sites, it might be 4, but I think it's 5 sites that are contributing NLP data, we will be able to release that table to you, the users. So we sort of have this rule that until at least 5 sites, and again, I think it's 5, it might be 4, are submitting a certain new data element, we don't release it just in order to make absolutely sure that there's very little risk of site re-identification. But as soon as that threshold is crossed, which should be relatively soon, that will be available. And we'll make sure to announce its availability so that folks know that it's there and ready to be looked at.
So I have a sort of a cross-cutting question, actually, to Brad and Maryam, and that is, obviously you have put together, really very impressive infrastructure and sort of data vetting, cleaning, and obviously such a thing could and should be used actually in the context of PASC and long COVID. Is that something you guys are tackling, or is that something where you might be looking for collaborations? What are your thoughts on that?
I mean, always looking for collaborations on all of this. Smart people working on hard problems is always a good thing, I think. But it's also, I know, something that's come up in our group. Dr. Hodder's brought it up a few times. So it's something that's kind of in the periphery right now. We're kind of pushing forward with a few different projects and starting to look at the larger ideas. So yeah, I think that's how this surrounds long COVID is a really interesting idea.
Right. I mean, I could imagine maybe some of your core infrastructure template being made into a knowledge store sort of object, and then being reused, obviously, with great credit in the context of this, because obviously the whole phenotype characterization of PASC is key. So if you're going to say, well, we're going to predict X with Y, you've got to characterize X, which is really a whole separate effort. But as you know, obviously you've done a huge amount of data wrangling and mapping, so that's something maybe could be explored offline. That's so great. All right, any other questions or thoughts? Great. Well, really interesting discussion and cool stuff, and we'll give you give the group 9 minutes back. So thanks. Have a good week. Take care.